So accurate surface wave measurements from below, principles and guidance. So measuring waves, what do you need to know? So this webinar basically is intended to, let me see here, I need to move the faces to another screen. There we go. It's basically to provide a basic understanding of subsurface wave measurements and how they're performed, and really give you a sense of what the challenges and limitations are going to be for the different techniques and the tools that you will be using. What is presented is really what we've learned over the last 20 years. And typically when I give these presentations, I like to share data to illustrate the principles, but because of the format, we're going to keep it short and not really have so much of that. So what you're really going to see here is it's really a trajectory of where we began with wave measurements at Nortek and where we ended up now. So you really see a full sense of how we've grown and improved the instrumentation over the years. So I'm hoping that once you're finished seeing this webinar, you understand how we measure waves from the subsea, know what the limitations are in choosing the correct instrument for your particular application. So waves, measurements, it's really observations. So what are the requirements? So what you need to understand, first of all, is that waves are a random event. What we experience, observe on the surface is a superposition of different waves. So if you look at this image, what you're seeing here is these bands of waves. So what you're seeing is waves, fields with different periods, amplitudes, and directions, all summed on top of one another. And this is superposition, and it allows us to make a lot of use the principles of linear math. So what you see at the surface, at the top here, is a time series. Is if you had one point right in the middle, for instance, let's say, and this would be representative of how we make measurements of waves at one point, and you see a trace of where the surface would be, and this is really what we're after. So measuring waves requires sampling over a given period of time so that you best capture or represent the complete sea state. So in order to do that, what we like to say is that you need about 100 cycles of the longest wave that you think you'll encounter. So if you're for instance, in the Mediterranean, waves might be about 10 seconds long. So you want about 1,000 seconds of wave measurements continuously sampling at, for instance, 1 hertz. And finally, the one assumption that we need to make during our measurement program here is that waves are what they call stationary. So that means they're not growing or decaying in that time that we're measuring for 1,000 seconds. Okay, what more should you know? So waves, if you look out in the ocean or been on the ocean, you know there's all different types of waves. So you have waves that extend from the very shortest, which are capillary waves that the wind generates, all the way to the longest waves, which are tidal waves, which are really driven by the sun and moon. What we're interested in are the wind-generated waves that we call the gravity waves. So when we say that, we're talking about this region right here. So this are waves from 1 second up to 30 seconds. You'll see that there's a bump here that shows the energy distribution that you might expect. And what we try to do when we're measuring waves is we're trying to capture as much of this bump as possible. So if you're cutting short, for instance, the short waves or the long waves, then you're not really representing the full wave field. So you could be risking underestimating the wave heights, for instance. So keep this in mind because I'm going to be actually referring to this later in the presentation. So what's below the sea surface? So this is where we're measuring. So you know the surface goes up and down as the wave propagates, for instance, from left to right here. And there's a signal below the surface. So if you go down in the water column and a wave propagates, you'll notice that it goes in this circular trajectory. And these orbital velocities are what permit us to measure wave properties of direction. We also have the pressure, which is a combination of the extra water height above the instrument. Say the instrument is down here at the bottom. So it's the extra hydrostatic and the dynamic pressure associated with these orbital velocities. So one thing that we know is that these behaviors are well described by linear wave theory. So that means that we can model and understand these quite well, have an analytic description of what it is. When we measure these down at the bottom, these properties of waves, these orbital velocities, we're not really measuring the waves directly. What we're doing is we're applying transfer functions and we're inferring what's going on up at the surface. I think the important thing here to notice is that you see that the orbital velocities, the amplitude of these trajectories that they go through, decay with depth. And this is determined by the length of the wave. So as the wave becomes shorter, the attenuation becomes much more rapid. And that's important because that means it's one of the limitations that we have to address when we're measuring waves. So why would you want to actually measure waves below the sea surface? You know that you can just throw a buoy on the surface and measure waves directionally, which is a good way to measure waves, but it does have its limitations. Many individuals want to measure from the subsea because it allows you to get away from fishing activity, vessel traffic, vandalism and theft, and they know that the process and the estimation is accurate. So that's why we do this. So where has it all started? The PUV method is where it really started many years ago. And basically what we're measuring is the pressure, which is the P, and two components in orthogonal directions of the orbital velocity, the U and V as it's referred to as. It's nothing new. It's been used for about 40 years now. And Nortek, I think, did this about 20 years ago when we first introduced the vector aqueduct profiler and aqueduct lines of instruments. And what I'm showing you here to the right is an aqueduct profiler. And you can see right above it, we have three beams projected outward, and we convert these into X, Y, and Z coordinates, or the U and V, and we measure the orbital velocities projected onto these two axes. And that gives us an indication of the wave direction. So the pressure, which is also measured from the instrument, allows us to estimate wave quantities that are non-directional. So these quantities are height and period. The combination of the P and the U and V allow us to estimate the directional estimates. So the peak direction, the mean direction, the spreading of the waves, and these sort of parameters. So the U and V, as I said earlier, it is the projection onto these two U and V axes, and it gives us an indication of the axis that the waves propagate on. And if you include the pressure, then it allows us to unwrap the ambiguity, which direction along this axis, and gives you an indication of the wave direction. So that's the PUV. But as I said, it's not without its limitations, and you recall this illustration from before. We saw the attenuation with depth of the signal that we're measuring. And if we were looking at what the restrictions are or the limitations, you can see that, let's see, if you have an instrument deployed at 5 meter depth, you'll notice that your minimum measurable wave that you can measure is about a 3-second wave, which is on the vertical axis. So all waves longer than 3 seconds, then you can measure at a depth of 5 meters. But if you move this instrument out to a depth of about, let's say, 20 meter, which might be excessive for this instrument, it means that the shortest wave that you would be able to measure wave quantities for would be about 10 seconds. So you can see that the penalty for moving it to greater depth is quite extreme. So this means for people using PUV method instruments is that you're either limited to very shallow waters, let's say 5 meters, if you want to cover the full spectrum of waves. We showed you earlier that we had that bump that we're trying to resolve in all the waves. So the gravity waves, we're trying to resolve as much of that as possible. If you're going to do that, then you really have to put it in very shallow water for these PUV instruments. Alternatively, you can measure just long waves, which is perfectly fine if that's your interest in your application, but that means you're only going to get swell if you're going to move it out to coastal depths. So you understand now that there's a limitation of what our instruments can measure for these PUV type of instruments. So we wanted to get deeper into the water deployment depths. without compromising how much of the wave spectrum we're going to measure. So we introduced some years later, a few years after this, what we call the Awak. And this was a current profiling instrument, and you'll notice that it has a center transducer. And this was really the key to getting us into deeper waters because it allowed us to echo sound to the free surface. So let me give you a little indication of how we do this. So the instrument basically got us into deeper water by doing two primary things. Instead of measuring the orbital velocities down near where the instrument was, we measured further up in the water column where the signal, those orbital velocities, were much stronger. So that helped the directional estimates. For the non-directional estimates, for the height and the period, we used what we call the AST, which is an echo sounding to the free surface. So we set a window around where the free surface was, and we echo sounded it, and we traced the surface of the ocean. And what's interesting is that this is a direct measure of where the free surface is. So we don't have to use any transfer functions to estimate what's going on. So this is what our signal typically looks like. And you can see here on the horizontal axis, we have signal to noise ratio, and this is distance. And this gives us, when we have such good signal noise ratio, we're able to get very high resolution of where the surface is down to sub-centimeter resolution. So it becomes a very accurate way to measure waves. But again, we're not without our limitations. So as you put the instrument into deeper and deeper water, you can see the spacing. If we're looking down on the instrument, the measurement points become greater, more and more spaced out. So if you looked on them from a side view, you can see that you have a distance between this AST measurement and one of the orbital velocity measurements. So there's a geometric limitation with deployment depth. So what we like to say is the shortest measurable wave is defined by the distance between measurements. So the cell separation must be less than half wavelength to be able to resolve that wave. I think it becomes much more clear if we plot this out. So what I've plotted here is the limitations with depth for the acoustic surface tracking and then the directional processing. So if we put this Awak out at 100-meter depth, you could see for the AST, we can measure parameters of height and period as short as 2 seconds, which is really great. However, if you looked at the directional processing, you're really going to be limited to waves that are about 6.5, 7 seconds long, and they have to be either that or longer to be able to estimate what the directions are. So you can see that really, if you want to get some meaningful coverage over the full wave band, you probably should shoot down towards about 50 meters or so. So as we said before, the PUV instruments, if you wanted to cover the full spectrum, you're really stuck down here at about 10 meters or less. With the introduction of this type of technology, we're able to move deployments out to 40 or 50 meters to cover more or less the full wave band of interest. So how do we get into deeper waters? I mean, that seemed to be our goal and where we're taking this technology. So what we want to do is measure waves from subsurface buoys. So you can imagine if you deployed an Awak on a subsurface buoy, what I'm showing you here, if you keep it 30 meters from the surface, which is a good distance to get good resolution in the wave spectrum, is that you could have a mooring that is about 90 meters long and have a subsurface buoy that is here to measure waves in the standard using these beams and the acoustic surface tracking. However, we couldn't just use the classic manner of just this array processing, which I'm not going to get into now, but we would have to convert these measurements from the beam coordinates to an Earth reference coordinate. So again, we're converting to a U and V measurement, and we combine this with the acoustic surface tracking, and that allows us to deploy this, make these measurements from subsurface buoys where the buoy is going to be rotating and we still have an Earth-referenced measurement system. And we call this the SUV method, where you have the surface and the two orbital components in the horizontal plane, the U and V. So it looks something like this, which is familiar to what our PUV was. The good thing about this is that we found out after introducing this, it really made deployments a lot easier as well. So the question we had to ask ourselves is, why are we relying on bottom frames to deploy these Awak instruments? We learned that you had the vessel requirements became reduced, so we could use small fishing boats of opportunity like this one, where we have 2 subsurface buoys and 2 Awaks, and these were deployed in 100 meters of water. And we can deploy in much more adverse conditions because you don't have to settle the frame on the bottom. And what it really became a kick over the side deployments. So this is how we would do it. We'd stream the buoy off the back of the boat, keep the weight on the boat, and then when we got on location, the site, we'd kick this weight over the side, and it would suck the buoy down to our location that we wanted to measure from. The good benefit also was that it ensured vertical orientation. And for those who have used divers in the past to deploy frames, you obviously don't need divers in this. So these are what I've explained to you so far is really development of the technology where we took ourselves from measuring rate at the bottom to making remote measurements and then deploying on subsurface buoys, which really allowed us to get into deeper and deeper measurements. Then some years ago came along the third generation of Nortek products, which we refer to as a signature series of products for wave measurements. And it really, it expanded on the capabilities of our measurement program. So the instruments that allow us to do that are the Signature 1000, 500, and 250. And these are really designed for different depths, deployment depths and different ranges to the surface. So what it really brought to you was broadband processing. So broadband processing really gave you a couple of things. The one was that you could use much less power for the same configuration as an Awak. So if you had an Awak, for a particular sampling scheme, you could expect to use 80% less power. And this means, it's great because this means that you can leave the instruments out for much longer times for service intervals. It also improved upon the directional estimates because there was much more uncertainty from ping to ping. So our estimates before, if you looked at it, there might be a little bit of variation from wave burst direction to wave burst. So if you're marching along from hour to hour, you would see a little bit of variability, and this reduces quite a bit. It also reduced it in what we call the spreading parameter, which shows the variability of the directional wave field. It also provided richer sampling when we introduced this, so the acoustic surface tracking now became 2 independent estimates of where the free surface was. And instead of positioning the orbital velocity cell up along the beams at some optimum position, what we do now is we make a small profile for each sample. And in post-processing, you can choose the level at which, in the position on the water column, where you want to actually do your wave processing. And then we have the 16 time slots for greater flexibility. So this instrument, I'm talking about wave measurements, but it can be used for much more than that. And that's what really the signature allowed for. So let me just mention this. I'm sure it'll be talked again about the signature series and other webinars, but let me just give you a glimpse of what it's about. So each second we have 16 time slots, and these different time slots can be used for different tasks. These are our pings, and this is the different types of functionality that you can use them for. So for our wave measurements, we are using the broadband velocity profile on 4 beams, and we're using the echo sounder altimeter data. So you can see where these fall within the time slot with some extra overhead. And this is sampling at 4 Hertz. So in summary, basically what I've tried to show you here today is that you have limitations with depth, but you can get around them. The first 10 meters of the water depth, you can use a PUV instrument if you know the limitations. But if you want to get out beyond that to 10 or 100 meters, you can use bottom mounted with the Awak or Signature series, so long as it has the acoustic surface tracking. But if you want to really get into deeper waters, then you have to put these on subsurface buoys and use what we refer to as the SUV technology. And of course, then you have the Signature series, which gives you a wider functionality with the current profiling, echo sounding, ice measurements, or what have you. So I'll leave it there and open it up to questions now.